for the infinite power tower that is shown in this example in the form of infinite exponentiation with the base 2 to the power negative 3 to the power negative 4 to the power negative 5, and this keeps going on as an infinite loop of exponentiation, we would like to see, does it converge? And can we find a quick way to deal with this infinite power tower and potentially solve it? To answer these questions, let's focus on the observed trend in this power tower. So as you can see, the base is 2, and then we raise it to the power negative 3 to the power negative 4, and so on and so forth. So let's focus on 2 to the power negative 3, and so on and so forth. So we have 2 to some real power, so it's a real number. Obviously, this is always greater than 0. So the first observation is the outcome should be a positive number. Okay, so let's now focus on the next base in the exponent. So we have 3 to the power a real number. So here is a real number. So if we focus on that, we can observe also the same thing. We can say, all right, we have 3. So let me write it here. So we have 3 as a to the power a real number, which should be a positive number. So if we negate it, we end up with negative 3 to the power a real number, which is highlighted here. And that means since we multiply both sides of an inequality with negative number, it should become less than 0. Now raise this both sides of this inequality with base 2. So we're going to have 2 to the power negative 3 to the real number that I highlighted here should be less than 2 to the power 0, which means should be less than 1. So that is one important observation. Then the answer we are looking for obviously is a positive number, but it's a positive number that is less than 1. So that's one immediate outcome. Let's continue this. So I can say, well, the same thing I can say about 4 to say a power a real number. So if I take a look at that, I can say, well, 4, negative 4 to the power some real number is going, like this one, is going to be less than 0. So as a result, 3 to such power, so I'm raising both sides of this inequality with a base 3, so it's 3 to the power negative 4 to the power a real number is going to be, so I'm going to write it just real, is going to be less than 3 to the power 0, which is going to be less than 1. So this is 1. Now I'm going to multiply both sides of this inequality with negative 1 to get this negative 1 that is shown in the actual infinite exponentiation. So I get negative 3 to the power negative 4 to the power real number should be greater than negative 1. And now I'm going to use a base 2 and raise to the powers on the left and right side of this inequality. So what I'm going to get is 2 to the power negative 3 to the power negative 4, and whatever is the exponent for 4 should be greater than 2 to the power minus 1, which means 1 over 2, which means 0.5. So great. What I learned here is this whole target, this whole number should be, not only we found it to be from 1, we found it to be a positive number. From 2, we found it to be less than 1. Now from 3, we found it that it has to be greater than 0.5. So this is number 3. Okay, so it looks like we are further and further zooming in. Now if we keep doing this, instead of, now let's say if I focus on base 4 here, and negative 4, so if I focus on base negative 5 here, it's actually 5 that is raised to the power negative 6 and negative 7 and so on and so forth, and then multiplied by negative 1. So if I focus on base 5, then I can do the same thing as I did here. I can say negative 5, so I'm going to write it here. I can say negative 5 to the power some power real number, which is minus 6, minus 7, dot, dot, dot. So I'm referring to this as some real number. It should be less than 0 because of the negative sign. So if that is the case, then I can use a base to raise it to the power of the numbers on the both sides of this inequality. I can get 4 to the power negative 5 to the power negative 6 to the power negative 7, so on and so forth, is less than 4 to the power 0, which is obviously 1. Okay, I'm going to construct this whole thing, so we need to multiply by -1, so minus 4 to the power minus 5 to the power minus 6 dot 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 should be greater than -1. So if I raise 3 to the power to the numbers, to the power of numbers on the two sides of this inequality, I get 3 to the power -4 to the power minus 5 to the power minus 6 should be greater than 3 to the power -1. And if I keep doing this, the next step here is I can write 3 to the power -1 as 1 over 3, which I'm going to do, but then I need to construct this minus here, so I need to multiply both sides by a negative sign. So again, it would change the direction of this inequality, so I get -3 to the power -4 to the power -5 to the power -6, and so on and so forth. Should be less than -1 over 3. Now the last step is using 2 and raise 2 to the power of both sides of this inequality. So I'm going to get 2 to the power -3 to the power -4 to the power -5, and so on and so forth, less than 2 to the power -1 over 3, which means 1 over 2 to the power 1 over 3. Side note, 2 to the power -1 over 3 is the same thing as 2 to the power -1 times to the power 1 over 3, and to the power -1 is simply 1 over 2 to the power 1 over 3. So hence this. Okay, so with this, I am arriving at this important outcome that 1 over 2 to the power 1 over 3 is here, this number, is 0.794. So interesting. The previous upper bound that we found was less than 1. The new upper bound that we found in equation 4 is actually less than 0.794. If we keep doing this for a few rounds, just basically, for example, next one, -6 to the power -7 to the power -8, and so on and so forth. So this whole thing is a real number. For the same reasoning is less than 0. So obviously then 5 to the power -6. So raising the 5 to the power of the two numbers on the two sides of this inequality basically will give us -7, and so on and so forth, less than 5 to the power 0, which is again 1. So if we keep this whole process going through this, we end up finding that 2 to the power -3, -4, and dot 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 for the actual target number. The infinite exponentiation will be greater than 1 over 2 to the power 1 over 3 to the power 1 over 4. So the interesting observation is when we start in the initial process, when we start with the base as a even number in this process, in this let's say reasoning, then we always end up limiting our target number in the form of lower bound limit. So we find greater than, so we find it to be, let me use a different color so that it's clear. We find the target number is greater than some lower limit, lower threshold, lower limit. Whenever we start with, say, as a start of the reasoning, we start with a base that is an odd number, we end up finding our target number to be less than an upper threshold or upper bound. In this case 0.794, and in this case if I just find the value for what is reported here, it's going to be about 0.591. So as we keep doing this, we are tightening the range. So next time we do this, for example, starting from -7, -8, -9, so starting the argument from there, the reasoning, and we keep doing so, we actually end up finding a upper limit or bound for the target number that we have in mind. So if we find it to be less than 1 over 2 to the power 1 over 3 to the power 1 over 4 to the power 1 over 5. And this is our new, in this process, this is our new, let's say, upper bound for the target number we have in mind. So this is our target number. I'm going to just highlight again. This is our target number. This is our new upper bound, which turns out to be roughly 0.74. So see, we went down from the upper bound, previous upper bound of 0.794 to 0.74, as we also previously went up from the prior lower bound of 0.5. So the prior lower bound was 0.5. It went up to 0.591. Last round I do before I show you a plot would be this one. So if we keep doing this, there you go. So if we keep doing -8, now we start with, again, even number, as you can see here. So we are dealing with an even number, and -8 to the power -9 to the power -10, and so on and so forth is less than 0. Therefore, rest of the argument, you raise 7 to such power, it would be less than 7 to the power 0, which means 1. You keep doing this down to the point you get to the desired target exponentiation, infinite exponentiation of 2 to the power -3, -4, and up, so on and so forth. And it's an even number. It would give us another, let's say, more tighter lower bound, which will end up to be, again, 1 over 2, 1 over 3, 1 over 4, 1 over 5, up to n to the power 1 over 6. And if this is computed, you will end up to see that this new, let's say, lower limit or lower bound is going to be roughly 0.623. So higher than the prior lower bound that we found, as was computed earlier, 0.591. So with this, you can see that as we proceed with these different lines of reasoning, we end up with tightening the upper and lower bound that we have in this example. And that is in line with what we see in this visualization. So in this visualization, what we are observing is, let me show you this observation that we have. So I have plotted what we see here. Here, this dot means 2 to the power -3, or basically 1 over 2 to the power 3. So the outcome obviously is 0.125. That is the y-axis, the value. The x-axis doesn't matter. It's just a matter of the fact that knowing it's a starting point. Correspondingly, if somebody is interested in starting from, let's say, the red dot, which is effectively 1 over 2 to the power of 1 over 3. So the difference between the red and the blue is the blue one is doing 1 over 2 to the power 3. In the red one, we are doing 1 over 2 to the power 1 over 3. So it would be somewhere close to 0.8. Initially, these two approaches end up with different initial values, but then they converge. So we go to, say, the next number, which is this one. Here we have 2 to the power -3 to the power -4, which is basically 1 over 2 to the power 1 over 3. So 1 over 2 to the power 1 over 3 to the power 1 to the power, let's say, 4. So it's close to 1. Close to 1. And you keep doing that. The next round is this number, which is 2 to the power. So I'm going to write it here. This next number is 2 to the power -3 to the power -4 to the power -5, which is 1 over 2, 1 over 3, 1 over 4 to the power 5. On the other hand, this one shown here is actually the number that is 2 to the, so let me write it this way. This number here is 1 over 2, 1 over 3, 1 over 4, 1 over 5. So the delta is whether we end with a number like 5, and the other method is whether we end up with a power that is 1 over 5. So as initially they are different, but then over time you see that the trend is a converging trend in terms of the outcome. So if we follow the blue lines, we see, let me use a different color, we see this sort of a trend line for whenever we are ending with the whole power tower with an odd number. So if we are ending with an odd number as an approximation of the target power tower, we sort of finding a dot that is on this sort of a curve. And these guys will not go above a level. As you can see, ultimately they all, for the lower level blue dots, they all converge to 0.658366. See, 0.85, so 0.658366. That's for blue ones, and the upper ones, as you can see here, so I'm going to show them. The upper blue dots are on a contour, or let's say are on a curve like this. So this curve on top is actually, as you can see, all converge to a y value of 0.690347. So 0.690347. Those are for the scenarios in which the power tower approximation ends with an even number. So there you go, 1 over 2 to the power 1 over 3 to the power 4, or you can think of it this way. For example, the next point here, I'm going to show it. This next point is when we have, so this next point is when we have 2 to the power negative 3 to the power negative 4 to the power negative 5 to the power negative 6. And so that's the approach. It just shows that this overall infinite power tower does not converge, because depending on we end or approximate the final exponent in the approximation as an odd power or as an even power, we sort of end up with a different value for the convergence of the power tower. See, we have two possible outcomes. One possible value is this one. One possible value is, so I'm going to highlight it, 0.690347. That's one possible outcome. The other possible outcome is 0.658366. So the short answer is this infinite power tower doesn't converge. It just has a bounded value. If there is a value to be defined, we would say this is a bounded power tower, infinite power tower, but not a converging power tower. It doesn't have a singular solution. And the interesting thing is the other approach, which is based on the red dots, would also converge to the same sort of a bound of 0.658366 and 0.690347, as you can see in this illustration, even though the methodology is different. Now we are doing, as you can see, 1 over 2 to the power 1 over 3. And for the next point, as you can see, 1 over 3 to the power 1 over 2 to the power 1 over 3 to the power 1 over 4 and 5, and so on and so forth. So for the lower ones, for example, let's say, if I change the color so that it's observable, let me put it this way. For this one, for instance, you're talking about 1 over 3 to the power 1 over 2 to the power 1 over 3 to the power 1 over 4 to the power 1 over 5 to the power 1 over 6. So as you can see, it's just different ways of trying to find an approximation of this infinite power tower, but they are all converging to same conclusion. If I zoom in, you can see this outcome now in a better fashion. So I have zoomed into this range, sort of this range, and when I zoom in that range, you can see that both the first and second method that are highlighted with the blue and red color dots are converging to the same outcome. Upper bound of 0.69347, doesn't matter we go with the blue or red, or lower bound of 0.658366, again doesn't matter if we go with the blue or red. Okay, I hope that this method of evaluating and analyzing this seemingly difficult infinite power tower that sort of try to show how easily we can find tighter and tighter upper limit and lower limit, getting close to actual numbers. See, with a few iterations down to, say, starting point of base of 8, we almost got there, because we found that the target power tower should be greater than a lower bound that is 0.623, and that is not that far away from the ultimate lower bound of 0.6583. So we are very close. With just few iterations we got there. And for the upper bound, when we were at the starting base of 7, so that we get to our target power tower, we found that it was upper bounded by 0.74. If we keep, and that is not that far away from the actual ultimate upper bound of 0.690347. So that's close. Alright, so I hope that this example is helpful in terms of showing how we can deal with this kind of problem, and the answer that basically is no, it's not converging, but it is bounded. Thanks for watching, and I hope this is helpful.